In this video, we're going to look at a special kind of case where it will be easy to show that the limit of a function of two variables does not exist. By analogy, let's start back and look at a function of a single variable. If we looked as x approaches a from the left, and we looked at the limit as x approaches a from the right, if they were not equal, if the two side limits were not equal, then the full limit as x approaches a of f of x does not exist, or did not exist, back in Cal 1. You might remember a picture of this, a jump discontinuity. If you've got limit values that exist on either side but are not equal, that was the picture that you might have had in your mind. An analogous situation in functions of two variables is, however, somewhat more complicated because when we're talking about a disk, we can approach the point AB in infinitely many different ways on an infinitude of different paths. To show that the limit as xy approaches AB of f of xy does not exist, it is sufficient to find two out of those infinitely many different paths, any two that give different values. If you can find two different approaches to the point AB that give two different limit values, then the limit does not exist. In Cal 1, there were only two ways to approach, two different values on two different ways. This is now in Cal 3, two different values along infinitely many different ways. It's sufficient to find two different approaches that have different values to show that the limit doesn't exist. So let's do that in example 3.2.2. We're asked to show that the limit as xy goes to 0, 0 of x squared minus y squared over x squared plus y squared does not exist. So let's try the simplest, maybe easiest approach. Let's try to approach 0, 0 along y is equal to 0. What does that mean graphically? Well, we know that we are looking at a function of three variables. So here's x, y, and z. We are going to the origin. We are examining in a disk around the origin. I'm saying let us approach the origin along y equals 0. So that means we're approaching the origin along the x-axis. That's one way, in fact, two ways, from the positive x and negative x directions to approach the point 0, 0 out of infinitely many different ways. If we approach along the line y is equal to 0, well, then our limits, so the limit as xy goes to 0, 0 of x squared minus y squared over x squared plus y squared is equal to, well, if y is equal to 0, we can plug in 0, which means that y is 0 for all of those values. So we're really looking at only when x approaches 0. When x approaches 0, if all the y values are 0, we get x squared minus 0 squared over x squared plus 0 squared, which is the limit as x goes to 0 of x squared over x squared. We can simplify. That gives us the limit as x goes to 0 of 1, which is just 1. If we change our approach now along a different path and we look along x equals 0, so looking along x equals 0 would be approaching along the y-axis. Right, so along x equals 0 is the y-axis approaching from either direction. Well, our limits, let me just save myself a little writing. Let's copy this. Our limit is now equal to the limit as y approaches 0. We're going to plug in x equals 0. So 0 squared minus y squared over 0 squared plus y squared, which is the limit as y goes to 0 of minus y squared over y squared. Simplify again. The limit as y goes to 0 of minus 1 is minus 1. So notice we've approached along two different paths, along the x-axis and along the y-axis, approached 0, 0 from two different ways and got two different limiting values. And so we can say that since the limit along two different paths gives two different values, the full limit does not exist. A question that you might have is, well, what does that look like in 3 dimensions? Do we have a picture like this? Is there a surface? Is there a jump in it? What, I mean, that could happen, but that's not what's happening here. So let's go and take a look at the function graph. So here in figure 3.3.3 is our function f of xy is x squared minus y squared over x squared plus y squared. It is, as you can see, kind of a tightly folded origami-like surface, but we can see exactly what's happening in our limit values. If we go along the x-axis, if we approach along the x-axis, right, in this direction, these directions, we got limit values of 1, and you can see that right on the graph. When we approached along the y-axis, so when we came in along the y-axis, and the same thing in the other direction, we got function values here that were equal to minus 1. But you can see actually the function is so tightly folded that you could probably construct a path and get to any value that you wanted between minus 1 and 1. So that is a strange picture that does not happen in functions of a single variable. So that's something else to add to your mental repertoire of the way function surfaces can look. We're going to do in the next video example 3.2.3 where we're asked again to show that the limit does not exist, but the paths that we have to choose are not going to be quite as easy to find.